Hello and welcome to the discussion sessions. Now, in our last session, I will remind you that we have started discussing the electrochemical machining process in the non-traditional machining. Now, it was told that electrochemical machining process is one of the important processes in the non-traditional machining processes. Here the unique feature of the electrochemical machining is that the material is removed from the workpiece and nothing happens to the tool, that means the tool does not wear out. Okay. So, therefore, the tool can be used repeatedly, all right. That is one of the very big advantages of the ECM process, that is electrochemical machining process. And the electrochemical machining process, therefore, this is the reverse of the electroplating, that was also told to you. Now, if you see the slides, electrochemical machining in this process, the electrolyte is pumped at a high pressure through the tool and the small gap between the tool and the workpiece. Okay. So, it is some kind of an electrolyte which is used, that is pumped through the either through the tool, or and if it is pumped through the tool, it goes within the gap between the gap between the tool and the workpiece. The electrolyte is so chosen that the anode is dissolved, but there is no deposition in the cathode, that is what is said. The order of the current and voltage are a few thousand amperes current, this is a high current, and low voltage, that is 8 to 20 volts. So, the operation is basically high current and the low voltage operation. Okay. Now, the gap is, that is the gap between the tool and the workpiece, is of the order of 0.1 to 0.2 millimeter. Okay. So, this is the standoff distance we talked about in case of abrasive jet machining and ultrasonic machining and so on. Okay. The material removal rate is typically 1600 millimeter cube per second for each 1000 ampere. Okay. Now, approximately 3 kilowatt hour are needed to remove 16,000 let us say millimeter cube of metal, which is almost 30 times the energy required in the conventional process. So, as you can see that here energy required will be very high. Okay. It is about 30 times the energy required in a conventional process. All right. Now, this is a schematic diagram of the electrochemical machining process. Here the electrolyte is passed through the tool, and this is isolated, okay, insulated, and this insulation is made because otherwise what will happen is this the material removal will be from the sides as well. So, we do not want that, therefore, the sides of the tool normally are insulated. Okay. Now, the material removal rate is independent of the workpiece hardness. Any kind of workpiece of any hardness can be used. Only thing is that the workpiece has to be conducting, and as we have said that it has to be, the workpiece has to be anode and the tool has to be cathode, and it is a low voltage and the high current DC supply is there. Okay. It become advantageous when either the work material possesses a very low machinability or the shape to be machined is complex. Right. So, hard to machine or it is a very intricate shape, then ECM is convenient or the advantageous. Unlike most other conventional and unconventional processes, there is practically no tool wear, that has been said, though it appears that since machining is done electrochemically, the tool experiences no force. The fact is that the tool and work is subjected to large forces exerted by the high pressure of fluid in the gap. That is the only pressure which the workpiece as well as the tool will be experiencing, that is because it is at a high pressure. So, that pressure is experienced by both the workpiece and the tool. This is more broadly the electrochemical machining, but otherwise setup, but otherwise the overall this is the same as in here. Only thing is that it is in details shown how the electrolyte is recirculated, taken from the tank, and how it is being recirculated, okay, after being filtered and so on. You can see it from here. Now, process parameters in gist it is the all have been said, but this is in gist. Only thing is that electrolyte we did not say that this is the either you can use the sodium chloride, okay, salt water, or NaNO3, okay, sodium nitrate. So, temperature will be normally 20-50 degree centigrade, all right. Flow rate is 20 liter per minute per 100 ampere of current, okay, and working gap is 0.1 to 2 millimeter. Overcut could be 0.2 to 3 millimeter. So, overcut I already said that this is when this is not exactly straight, the hole is not exactly straight, okay. And the surface roughness is about 0.2 to 1.5 micron. So, you can see that the surface roughness is good, all right. Electrode, that is a tool material that can be copper, brass or bronze, because the tool does not wear out. So, it can be a soft material like this. Now, electrochemistry I will not go into very details, that follows the Faraday's law of electrolysis. Material removal is proportional to the current, time and the E, okay. So, E is the gram chemical equivalent, which is A by Z, and you can find out that what is the material removal of the process, okay. So, this since this follows the Faraday's law, all right. So, F is the Faraday's constant, okay, and Faraday's constant will be given in the handbook. So, if you find out the time, the gram chemical equivalent, that can be found out from this, okay, atomic mass of the anode and the valency of the dissolution of the anode. So, the E will be known, time you know, you can note down, find out what is the current which is going through and divided that by Faraday is constant, that would be the material removal, and the material removal rate will be I E divided by F, because this divided by T. So, T is getting cancelled here, okay. Well, MRR also can be obtained like that, but here it is not very important, we are not going into details. So, what is important for you to understand is that this is the one I E by F, that way you can find out the material removal rate, this is more important, okay, because through the density also you can find out, of course. So, this is what it is said here, that this is the density of the anode, volume of material removed from the anode in time and area, okay. So, this is in details that you can simplify and finally find out how the material removal rate can be expressed. But as I said that this will be enough for you to understand that this is the simpler way of finding out what is the material removal rate, okay. Now, let us discuss a little bit about the electric discharge machining, and we said in the discussion that electric discharge machining is a thermal process, where a very high temperature is produced between the tool and the in the gap between the tool and the workpiece, and that temperature actually removes the material by melting and sometimes evaporating, okay. So, this is the mechanism, that is here is the tool which is cathode and workpiece is anode again, all right, and between these two there is an ionized column which actually makes an flow of avalanche of electrons from the tool to the workpiece side, okay, as the current is passed between the tool and the workpiece. So, here is more details. So, what happens is when the current is established, proper current is established, then the electron moves from the tool at a certain speed towards the workpiece, okay. So, on the way to its movement, this meets the ions of the dielectric fluid or molecules of the dielectric fluid, dividing these molecules into ions and the electrons. So, those electrons again rush towards the workpiece, okay, and on the way they meet the molecules of the dielectric fluid, breaking them into ions and more electrons. So, that way the electrons keep on getting formed, okay, and ultimately what will happen, that there will be an avalanche of electrons, okay, and that avalanche of electron while moving from the tool to the workpiece side, it will look like a spark, okay. So, that creates a very high temperature, and that high temperature at a very tiny spot of the workpiece will melt and can evaporate the workpiece, okay. All right. So, mechanics I have already explained it to you that the local gap between anode and cathode varies due to the asperities. So, electrostatic field is created at the minimum gap due to the voltage. Okay. What we mean to say is that suppose this is the tool, okay, and this is the workpiece. Okay. In between there is a gap. So, this distance is the nearest distance. So, here this thing will happen that I already explained, that electron will flow and it will meet the molecules on the way, because here you have the dielectric fluid, okay. And normally this is kerosene or some kind of a mineral oil, all right. So, once it happens, then at the high temperature the material is lost from here mostly, and a bit of from here, because the ions are moving towards the tool. Then the minimum distance will be somewhere else, and the same process will take place until around the entire area that avalanche of electron is seen. Okay. Electrostatic field is created, it causes cold emission of electrons from the cathode, liberated electrons accelerate towards the anode. Okay. Electrons collide with the molecules of dielectric fluid, breaking them into electrons and positive ions. Ions will move towards the tool and the electrons will move towards the workpiece, bombarding the workpiece surface and removing the material. So, that actually is the cause, that is because of the high temperature also. So, produced electrons dislodge more electrons from the dielectric molecules. A narrow column of ionized dielectric fluid molecules is established in the gap connecting the two electrodes. Okay. Now, this temperature at which this avalanche or the electrons when they are hitting the workpiece at that moment, the temperature can create up to 10,000 to 12,000 degrees centigrade. Okay. That spark. So, that causes work material to melt and evaporate. All right. Here is the schematic diagram. This is the tool which is made as anode, and this is the cathode which is the workpiece. Okay. Workpiece is plus, tool is the minus, and in between we have the gap, this is the interelectrode gap, okay, and current is passed through this. Okay. So, when the current is passed through the tool and the workpiece, then the avalanche of electron will be shown in this, will be seen in this gap between the tool and the workpiece, okay, creating the temperature, very high temperature to remove the workpiece material. All right. Here what happens in if we compare it with the electrochemical machining, in electrochemical machining we have seen that nothing happens with the tool, okay, no material is removed from the tool. But in case of EDM, electro discharge machining, the tool wears out because the heavier ions will hit the tool, okay, it will go towards the tool. So, therefore, in that case the tool also wears out. Of course, it wears out much less than the workpiece, but nevertheless in comparison to electrochemical machining, in the electro discharge machining the tool of course wears out. Here is the material removal rate in the EDM process. So, we may not go through this very in detail. So, what I mean is that there are simple formula which are readily available in the textbooks. So, that can be used for finding out the material removal rate, okay, through the energy that is available as the heat at the workpiece. All right. And finally, you can find out the formula through this energy by equalizing this, that this is the formula where all these things will be given and you can find out what is the material removal rate. We are not going into that details because this of course is not under the purview of this course. All right. Here I have shown it to you already that this is the for electrochemical machining. Okay. Here it is, I am repeating because for the electro discharge machining, this is what we can actually get using the electro discharge machining, and this, as I was telling, that this is for the using the electrochemical machining. If you remember, I said to you, I showed it to you saying that these are the turbine blades where the holes of very complicated shapes can be drilled. Now, advantages that any material that is electrically conducting can be machined by the electro discharge machining. Materials, regardless of their hardness of course and the strength, can be Okay, whatever is the toughness, whatever is the microstructure can be easily machined by the EDM, because as you understand that these properties of the material no longer stand on the way, because it is only the avalanche of electron, it is temperature is so high that any material can be melted and evaporated. Okay, 15,000 degrees centigrade as we said, and it is on the very tiny spot. So, therefore, in the vicinity you will not have any kind of heat affected zone, because it is for a fraction of second at a very tiny zone, and the material immediately goes off and this spot cools down and the spark happens on the other spot, where as I said the distance between the asperities will be minimum. Okay. The tool and workpiece are free from cutting forces. Okay. Edge machining and sharp corners are possible in the EDM process. The tool making is easier, as it can be made from softer and easily formable materials like copper, brass, graphite also in this case. Like in case of ECM also we said that the copper, brass also can be used as the ECM tool material. Okay. But here the graphite can also be, graphite is also used for making the tool in the EDM. These are the other advantages. The process produces good surface finish, hardened workpieces can also be machined. Okay. EDM is a bar free process. When the EDM is used, there is no bar formed. Hard die materials with complicated shapes can be easily finished with good surface finish and accuracy. Due to the presence of dielectric fluid, there is very little heating of the bulk material. As I said already, the mechanism, because it happens at a very high speed, and in the sense that very high time taken for the spark to happen is is a very small. This is 1 upon maybe 1000 in seconds. Limitations of EDM is the material removal rates are low, making the process economical only for very hard and difficult to machine material. It takes longer time, of course. Recast layers and micro cracks are the inherent features of the EDM process. Okay. So, recast layer is the layer which is the hard layer, and this is also known as the white layer, and this is a disadvantage of the EDM, that when the EDM process happens, that some of the molten material comes and precipitates on the surface, and it is a recast layer, it is a hardened layer, and that has to be removed. Okay. Now, the EDM process is not suitable for non-conductors, of course. Rapid electrode wear makes the process more costly. Okay. This I have already mentioned, the tool wears out. The surface produced by EDM generally have a matte type appearance, requiring further polishing to attain a glossy finish, meaning the surface finish is not very good. Okay. This is the surface finish in EDM. This is how you can actually see the surface is produced, because these are the sparks which happens in spots. Okay. This is of course highly exaggerated. This is the tapering and the overcut. This is the when it is not insulated, the sides are not insulated, this is what may happen. Okay. Because the process avalanche of electron, formation of avalanche of electron may happen from these sides also. All right. So, therefore, it is insulated, and in that case the tapering can be prevented. Okay. Application of EDM is a hardened steel dies, stamping tools, wet drawing, and the extrusion dies. Okay. Then we have the headed dies, forging dies, intricate mold cavities, and such parts are made by the EDM process. Of course, the process is slow process, as I said, but nevertheless these are the materials. Okay. Materials are very hard, okay, very tough. So, by EDM it is convenient to produce these parts. The process is widely used for machining of exotic materials that are used in the aerospace and automobile industries. This is simply because those materials are hard to machine by the conventional machining or any other process, by the way. EDM being a non-contact type of machining process, it is very well suited for making fragile parts that cannot take the stress of machining. This I said already in the introduction, that in the as a drawback of the conventional machining, that you cannot have a very fragile part machining. Okay. But here there is no contact between the tool and the workpiece, and therefore fragile parts can be machined. This is what it is said. All right. Deep cavities, slots and ribs can be easily made. Micro EDM process can successfully produce the micro pins, micro nozzles, micro cavities and so on. This is a type of the EDM process, that is the electro discharge machining, and this is called the wire EDM, because a wire is used as a tool for the EDM process, and that wire actually is continuously being, it is not only the, it is not the stationary wire, but it is continuously moved. So, this is used, wire is used as a tool, okay, and this is the workpiece. So, in this case you can see that if we can move the workpiece or the tool, a contour can be machined, okay, which is difficult in case of the normal EDM. So, this is a special form of EDM that uses small diameter wire as electrode to cut a narrow curve. Curve is this. Okay. Now, here you can say that, see that there is a spool, okay, and here the dielectric fluid is passed through the nozzle. This is the wire electrode, this is the work, cutting path is here, all right, and the feed motion in this axis. It can be moved in this axis or in this axis, or jointly it can be moved also to make a very complicated contour, all right. Now, operation of wire cut EDM is, I already told you that CNC can be used for motion control, for example, okay. So, for very complicated shape. While cutting, wire is continuously advanced between the supply pool and the take up spool, all right. This is the supply pool and this is the take up pool. While dielectric required using the nozzles directed at tool work interface or submerged work part. So, it can be either submerged or the dielectric fluid can be injected here in the working zone. This is the schematic, it is a enlarged part, this is the curve. So, this is the wire, okay, and the slot is being made, you can see this. So, this is the overcut. Okay. Application is ideal for stamping die components. Since curve is so narrow, it is often possible to fabricate punch and die in a single cut. Okay. You understand that from a material, okay, so square plate, if you cut it from in the middle with a complicated shape, that is the punch. So, the rest of the thing can be used as a die, all right. Other tools and parts with intricate outline shapes such as lathe form tools, extrusion dies, flat templates, okay, this can also be used with using the EDM. Now, next is the thermal micromachining processes. Now, the electro discharge micromachining is one of them. Now, electro discharge machining we have seen. So, electro discharge micromachining is the miniature version in one word of the electro discharge machining, because the principle remains the same, and the principle I have already discussed, that how this avalanche of electron is generated, because this is the electron dividing the molecule of the dielectric fluid into ions and the more electrons and so on. Now, other processes are the laser beam micromachining, electron beam micromachining, ion beam micromachining, all right. So, ion beam, except ion beam, others are of course the thermal processes. Ion beam is not counted as a thermal process, because here the temperature occurring is not high, all right. These are the schematic diagrams of the ion beam, all right. This is the electron beam, this is how it happens in the, as in case of the electro discharge machining. This is the laser beam machining, all right, and the laser is used for heating and removing the material. So, therefore, all these are the thermal processes. Okay. So, I will describe some of them. For example, electron beam machining. In electron beam machining, there is an electron gun. Okay. Electron emitting, this is hot tungsten filament, and when the high voltage is passed through this circuit with the hot tungsten filament, then the electron beam is emitted. Okay. So, that electron beam can be concentrated and moved, all right, with the help of the electromagnetic lens and the beam control coil. So, electromagnetic lens will concentrate the beam of electrons, okay, and the beam control coil will move the beam if a contour has to be machined or contour has to be made on the workpiece surface. So, here only thing is that electron beam machining has to be done in a high vacuum chamber. So, it is about 10 to the power minus 5 millimeter of mercury. So, this is because otherwise electron beam will collide with the molecules of the air and their energy is lost. So, therefore, this is a disadvantage of the electron beam machining, that each time you have to make another part, you have to open the chamber, take out the machine part and put the new part. So, in that case again you have to make the vacuum, and the vacuum is quite high, this is 10 to the power minus 5 millimeter of mercury. So, therefore, this process becomes a little inconvenient and expensive as well. Here I have already told you that how it is done. These are the quantitative measures, that is the electrons to about 75% of light speed acceleration. Beam is focused through the electromagnetic lens, reducing diameter to as small as 0.025 millimeter, 0.025 millimeter. This is the spot. On impinging work surface, kinetic energy of electrons is converted to thermal energy of extremely high density, which melts and vaporizes material in a very localized area. Application is ideal for micro machining, drilling small diameter holes down to 0.05 millimeter, cutting slots about 0.025 millimeter wide, drilling holes with very high depth to diameter ratio, and ratios can be as greater as big as 100:1. So, you can see that this is actually advantage over the conventional machines, there it is very difficult actually. This is the laser beam machining diagram, another diagram that you can find. This is the laser gun, this is being concentrated and the putting it on the workpiece, this we have already discussed. Laser is the light amplification of stimulated emission of radiation, this is the laser stands for, and the laser converts electrical energy into a highly coherent light beam with the following properties: monochromatic, theoretically single wavelength in the case of laser. So, here as you can see that how it is different from the electron beam machining is that it can be actually, if you have a laser gun, it can be machined, it can be used on the air, in the air. So, it is air does not interfere, the molecules of the air do not interfere with the. So, this is the laser light beam and the lens will concentrate at a very tiny spot where the energy of that will be very high, so high that it will actually create very high temperature to melt and evaporate the workpiece material, irrespective of the strength, hardness of the workpiece material. These properties allow the laser light to be focused using optical lenses onto a very small pot with the resulting high power densities. Applications: drilling, slitting, slotting, scribing and marking operations, drilling small diameter holes down to 0.05 millimeter, 0.025 millimeter, and generally used on the thin stock, because otherwise those are otherwise very difficult to machine because they are very thin, fragile. Work materials are metals with high hardness and strength, soft metals, ceramics, glass epoxy, plastic, rubber, cloth and wood. So, on these materials we can use the laser beam machining for machining. This is another process which is called the plasma arc cutting. So, here it is the plasma which is created by the tungsten electrode here again, and the plasma arc has the primary gas, the column, and the secondary gas column that protects that. This is a standoff distance, and this is the plasma arc torch, and here also it is actually it creates very high temperature, and with that high temperature the material is melted, and the molten material is removed from here. This is the curve which is being made. This is the slot or the groove or the curve, in a different way it is called. Alright. Plasma, this is a superheated electrically ionized gas, and the temperature is 10,000 degrees centigrade to 14,000 degrees centigrade. As you can understand that at this temperature any material can be melted and evaporated. So, it is actually it really evaporates the material because it is such a high temperature, but it is at a small spot. So, therefore, once again I repeat that in the vicinity there is no heat affected zone. All right. Plasma arc generated between electrode in torch and anode workpiece. The plasma flows through water cooled nozzle that constricts and directs stream to desired location. Okay. So, these are the processes that I basically wanted to discuss with you to give you a basic idea about the unconventional or non-traditional machining. Okay. Now, we will start a new chapter in this lecture series. Okay. This topic is now computer numerical control. Okay. Now, let me give you a preamble about the computer numerical control. Of course, we will be having a hands on training in the laboratory. Okay. I will take the shots in the laboratory and we will show you the entire video of how the programming can be made and how the machines can be operated using those programs. Okay. So, that will be in details I will be telling you. Also, I will be showing you in a PPT separately before we go to the lab. But here what we are going to discuss is that what the NC and the CNC machines are. Okay. What is the difference between them? How the why the NC and the CNC machines they come into picture? Why we need them? All right. So, to tell you briefly, like when we use the conventional machining machines, okay, you must have seen that there is a prime mover, and that prime mover actually gives the movement to all the parts, in the sense that it will move the spindle, it will move the lead screw, okay, for the feed, and the feed motion will be taken from the gear drive, gear train in the headstock and so on. So, there is one prime mover and you will not have much choice of the relative movement between the tool and the workpiece. All right. Now, as a result, what happens that a particular machine, there you cannot have the possibility of changing the configuration of the part. Okay. Meaning that suppose you take an example of the turning lathe. All right. In a turning lathe, you cannot cut the gear teeth. Let us take that example. All right. Or vice versa, in the case of the milling machine, all right, you can make a flat surface, you can make a you can cut gear teeth, but you cannot make a cylindrical surface. For that you have to have the turning lathe. This is because the configuration of the machine is such that you will have a particular relative movement between the tool and the workpiece, by means of what you have the only certain types of the surfaces that can be made. Okay. So, as a result, in one word what we are having is that the conventional machines, they are fixed. Okay. You cannot have the flexibility. Now, as long as the mass production is concerned, that you are producing one particular part in a very large number, this is okay. All right. But if you have to change the configuration of the parts, and if you have to change the types of the parts or the types of the product that you are producing, which we call as the batch production, for example, in that case those machines will not be cannot be utilized that you are using in the mass production. All right. Then you have to have machines which will offer you more flexibility, that is that using one machine you can have different kind of configurations. Okay. For that purpose, we had the these machines, that is the numerically controlled machines and the computer numerically controlled machines, they have been invented way back in about 1950s, when in about 52, 54 the prototype came from the Massachusetts Institute of Technology, and the it was introduced somewhere around 1955, 56, something like that. Okay. Whereas in 1960 this has already been started being used in the FMS, that is flexible manufacturing system. So, you can see that with the invention of the CNC and the NC machines, our possibilities have increased, and the very rapid growth has taken place from the time the NC and the CNC machines were invented. Okay. And that has made a revolution in the process, the machining, okay, in the manufacturing. So, if you see the slides here, computer numerical control. So, here manufacturing auto operator, he already has much less responsibility, much less work, in the sense that he will only be an observer in this case. Okay. So, he will actually numerical data, he will put it in the numerical controller as the numerical control, using the numerical control code. Okay. So, this will actually drive the machine, and the machine will produce the part. Okay. So, this is the action, that means here it is the brain, it will actually read the data that the operator is putting here, it will interpret what the data means, and this, by interpreting this, it will send signal to the hardware, that is the machine, what to do. Now, now let me tell you that how this flexibility can be obtained. So, as I said that in case of NC and the CNC machine, we can have the flexibility. Okay. That means we can change the configuration of the parts. This is possible to have, instead of one prime mover, we can have the motors for each of the 3 axes X, Y, Z. Okay. Nowadays, of course, there are 5 axis machine. So, there are more number of axes, but let us consider to begin with the 3 axis X, Y, Z. Okay. So, if we have 3 different motors for movement of these, independent movement of each of these axes X, Y, Z, then we can move them as per our requirement. We can move them one by one, we can move them simultaneously, we can move 2 of them simultaneously to make any kind of surface or any kind of relative movement between the tool and the workpiece. You understand that? That will be then that will make the flexibility possible. That means we can have the change in the configuration of the parts, we can make any kind of parts using the same machine and so on, which will differ from the machines that we are used to see in the as conventional machines. Okay. All right. So, if you look at the history a little bit, around 1955, the dates that I mentioned, John Person and the US Air Force defined a need to develop a machine tool capable of machining complex and close tolerance aircraft parts, okay, which will actually have the repeatability. Okay. So, about 1959, the Massachusetts Institute of Technology announces automatic program tools, okay, for programming language. So, this also has a concept, they also came up with the concept of the computer numerically controlled process, all right, and then they have offered the programming, that is the automatic programming. In about 1960, there is a direct numerical control which came into picture along with the FMS. FMS also came around this time. This eliminates the paper tape punch programs and allows programmers to send files directly to the machine tools. Okay. So, earlier, prior to that, the paper tapes used to be used for the programming. So, from 1960, it is the direct numerically controlled, when the program could have been directly input to the machine tool. Okay. Now, the computer numerical control therefore is a form of programmable automation in which the processing equipment is controlled by means of numbers, letters and other symbols which are coded in an appropriate format to define a program of instructions for a particular work part. Okay. Now, there are different types of numerically controlled. It can be NC, that is conventional numerical control. It can be direct numerical control, DNC, or the computer numerically controlled, CNC. Okay. In the direct numerical control, when we say this is actually the manufacturing system in which the number of machines are controlled by a computer through a direct connection and in real time. So, if you see this, here there is a central computer. Okay. Now, the bulk memory NC programs are kept in the central computer. So, this bulk memory will have the program for all these machines, okay. And all these machines are connected to the central computer by the electronically or electrically. Okay. So, so that from the central computer the program can be sent to the individual machines. Okay. So, these are the telecommunication lines, all right, and the feedback from the machine can also be obtained to the central workshop, central computer, all right. So, meaning that status of each of these machines can be found out from the central computer, and the individual programs what this an individual machine is supposed to do, that will be sent also through the central computer, from the central computer. Okay. So, that means there is no it is not required to have the computer system standalone system for each of them individually. It is a bulk memory NC program, and those programs are for all these machines, and individual program can be given to a particular machine. This is the direct numerical control, and this is the first time, as I said, the milestone is the 1960. Prior to that, it was of course the paper tape which used to be given to each of these machines individually. Okay. So, this is the first step which came in about 1960, that it is directly given to the machines. Okay. And there is a bulk memory program for all the machines, and individually the machines can be given. You do not have to have a standalone system. Okay. All right. Now, computer numerical control with reference to the or in comparison to the DNC, that is the direct numerically control. Here we have one system, okay, that is it is an NC system, numerically controlled system, using a dedicated microcomputer as the machine control unit. So, machine control unit actually will have a dedicated microcomputer. Okay. The conventional NC controller unit is a hardwired, that is control features cannot be easily altered to incorporate improvement into the unit. So, here what you see is that tape reader, okay, this is for initial program entry. Tape reader is something where the program is made and program is kept. Okay. So, program is prepared in a certain fashion. I will tell you how this program can be made when we discuss the part programming, all right. And this program is read once by the tape reader. Okay. Now, the NC program storage will store that program when it is fed here, and this is the microcomputer, this is software function. It will actually read and interpret what to do, what this program says, line by line it will read and interpret, and accordingly it will send the signal to the computer hardware interface and the servo system. Okay. So, here we have the interfacing which actually then sends the signal to the machine, that in which axis, as I said, that we have individual motors to different axes. So, to different axes we send the signal by the computer hardware interface, depending upon the program, depending upon what we want to perform according to the drawing, okay, how we want the tool to be moved or workpiece to be rotated with the in the spindle and so on. So, this in details I will tell you little later. Advantages of the computer numerical control, these are this reduces the time for delivery of the part, of course, reduces scrap rate of material. Why the scrap rate of material is reduced? Because here the wastage is very less. Okay. Now, the program is made, and if we are sure that the program does not have any mistake, because we can actually run the program idly, in the sense that we can simulate the program. I will show you how to simulate it, and then that program, if we run in the machine, there will be no fault because we have already tested it, and all the parts will be made according to the program and they will be identical. So, there will be no wastage. So, therefore, there will be the scrap rate will be much less. This is very important when the raw material is very expensive. Okay. If the raw material is expensive, then the scrap rate is very expensive. So, if we lose, if a part is rejected, then we lose lot of money in that. Now, that reduces the tooling cost also, because here the tooling cost is not much in case of CNC. Reduces layout time. Layout time is that where you have to plan that where the machines will be kept and how the machines will be kept. So, here it is not required. Increases the machine and tool life. Therefore, the tool life increases and the machine life increases because everything is optimum. Okay. I will show it to you later at a later stage that how the machine itself can optimally calculate the optimum parameters, and it can always work with an optimum parameters. So, therefore, the tool life is maximally used. Tool is maximally used to have its life maximum. Okay. So, is the machine. Reduces storage problems, okay, because we can have the time very fixed time, that when how long it can take, okay, and exactly that much time it will take. So, therefore, storage will not be required then. Less setup time, okay, as I said that layout time also will be less, tooling cost is less, and the setup time accordingly will be less. Reduces actual machining time, because again it is optimally done, all right. Allows rapid design changes in the part, because once you change the design, that means that you have to change in the program. So, you just make a change in the program and then the program will be accordingly working, and the change in the design will be incorporated in the manufacturing, in the fabrication. Okay. Less jigs and fixtures are needed. So, this already I said, that reduces tooling cost, all right. Here is the principle that I said. So, let us say we have x and y axis or x and z axis as we said. So, this is a turning, all right. In the turning, we have the cylindrical jog which is mounted on the 3-jaw chuck here, and this is the tool on the tool post, all right. So, let us say the tool can move apart from the rotation of the workpiece which is on the spindle. So, it will be rotating. The tool can move along this axis, that is the feed, when the feed is given. Okay. So, this axis in the turning is the x axis, okay. And this movement of the tool, all right, along the axis of the parallel to the axis of the workpiece is the z axis. This is particularly for the turning. I will show you for milling and drilling, but for turning this is the system of axis which is internationally accepted. Okay. And mind it that these machines are used all over the world, and we can get a machine which is from Germany or which is from USA, and there also they have to use this kind of coordinates, otherwise the movement will be erroneous, it cannot be correct, and the fabrication of the parts can be erroneous, all right. Okay. Now, here if you see that two individual motors, one stepping motor here which is for the movement along the x axis, okay, in this direction, and this is another stepping motor which is used for moving the tool, okay, on the lead screw. This is in the z axis. So, this stepper motor is to move the tool along the or parallel to the axis of the workpiece, and this is perpendicular to the axis of the workpiece, all right. Now, here is the program, that program is made, all right, and that program is run through the program reader. So, the program is read in the program reader, it is being decoded, okay, and after being decoded it is amplified, okay, and it is sent to both the stepper motors which is in the z axis or in the x axis. So, So, according to the program, whatever is given in the program as instruction, each individual stepping motor, okay, they will understand that what is to do, how to move, because this is the decoder, it has read and interpreted accordingly according to the program and send the signal. So, if both the stepper motors move simultaneously, you know that it will be movement like this. If only this stepper motor moves, the tool will move like this. If only this stepper motor moves, the tool will move like this, and so on. So, by taking the signal either to this stepping motor or sending to this stepping motor, we can actually have different kind of movements of this tool. All right. So, once again, from the program, through the program reader to the decoder actually decode the program. So, what we want actually, and sends the signal to one of these amplifiers. This signal will be amplified and sent to the stepper motors, and the stepper motor will move. So, you can see that there is not a one prime mover like in the conventional machine. So, since there are individual motors for the individual axis, in this case it is the turning process x and z axis, as I said. So, therefore, we can have any kind of relative movement between the tool and the workpiece. So, to make a cylindrical surface, or it can make another movement to make a contour, for example, and so on, that we will see in the lab also. So, here what is visible is the program reader. This is the line diagram of this shown here, buffer storage. Okay, this is the program medium. This is what we have created. You have created this program medium. That means you have to make the program either on the you have to store it. So, these days of course, the program is made in a very different way. So, this is the program medium, which is the old example of when the program used to be made on a tape, okay, on a paper tape or on a magnetic tape and so on. But these days you understand that we have the memory sticks, we have the direct input to the machine and so on. So, this is the buffer storage. Buffer storage stores the program, okay, for a part of the program. Let us say this decodes, amplifies, and after amplification, like in here, it will actually drive in the x direction. Okay, drive in the x direction will be here, all right, or it will drive in the z direction. Z direction is this, all right. So, it will be sent to this stepper motor or this stepper motor, okay. And this is the operative member. Operative member is this, all right. In this case, it is the system of the workpiece and the tool. Okay. Now, major components related to computer numerical control machine tools, these are the following. Any computer numerical control machine tool, okay, essentially consists of the following parts. So, as we have seen that major thing is the part program. So, how you will program the part, meaning that you have to fabricate a part. Okay. So, in conventional machine, what we do? We make a technological chart. That first stage is we have to face. Let us give an example, take an example. We have to face a cylindrical job, okay. Then we have to turn the cylinder, all right. Then we have to rotate that the fixing from the other end, and then again face it, all right. Then again turn it, and probably then make steps, then groups, then holes and so on. So, there is a particular sequence of operation that we write down in a piece of paper, okay. Okay. So, that will be the technological chart, which will dictate that which process to be performed first. This is very important when the process is very complicated, because depending on the sequence of processes, we have to put the machines. Now, in one part, it is not only the turning, it may involve the drilling operation, or it may involve the milling operation. Okay. In that case, the part has to be routed, okay. Part has to be moved from turning machine to the drilling machine to the milling machine, depending on the sequence that you have made. sequence of operations that you have made. Okay. Now, suppose there are many of such parts, all right. Some of them will require drilling, some of them will require milling, some of them turning and so on. So, that layout in this case is very important, that the all milling machines will be together, or all drilling machine will be together and so on, or according to the sequence the machine's layout can be planned, so that the time is not wasted in the routing, and time wasted means the production loss. That means the time required will be more and the production rate will be less, because production rate is 1 by time that we said. Okay. Now, let us see part program. Part program is a series of coded instructions required to produce a part basically, all right. So, what are those coded instructions, and for what type of machining, for that we will discuss later. Now, part program controls the movement of the machine tool and on off control of auxiliary functions such as spindle rotation, coolant. Okay. For example, you have to you are fixing that part, okay, or you are mounting that part on the 3-jaw chuck, then you have to tighten it, okay, clamp it, then only the switching on the rotation of the spindle. So, in the program you have to be very specific that the spindle will be rotating, and rotating clockwise or anti-clockwise. In both ways the spindle can rotate. So, depending on the program, depending on your requirement, the spindle can be rotated according to the program, and it can be program can be written that the spindle is going to rotate clockwise or anti-clockwise. Okay. The coded instructions are composed of letters, numbers and symbols. Now, by coded instructions we mean that what will be the overall, what will be the relative movement between the tool and the workpiece. Okay. Now, or the coolant on off or the spindle rotation, all these are coded instructions. All these have to be, comments have to be given in the coded instruction. For writing the coded instructions, we said that we can use the letters, the numbers and the signs. Letters, all 26 alphabets of the English they are used. Okay. Numbers used 1, 2, 3, 4 up to 99. Okay. And the signs like plus, minus, meaning that you find out that z axis, you tell z axis and then you write the dimension, okay, or the how much it has to move with a sign minus, meaning that according to the selected system of axis, whether it will be moving to the right or it will be moving to the left. Okay. So, these details or these particulars we will be looking at a later stage. All right. Now, they are composed of letters, numbers and symbols, as I said. Next is the program input device. So, this is also one of the components of the CNC machine tools. All right. Now, input device, program input device is the means for part program to be entered into the CNC control. Now, 3 commonly used program input devices are punch tape reader, magnetic tape reader and computer via RS-232C communication. So, this is the latest one, whereas the punch tape reader or magnetic tape, they are pretty old. Okay. So, the rest of the material I will discuss in my next session of discussion. Thank you very much.